Welcome, folks. I just want to talk to you about heat and calories. What is heat? What are calories? What do they measure? And this should tie in well with our calorimetry lab that we just did. So let's go ahead and go over the answer or go over some important pieces of it. Okay, so heat. You hear the term a lot, and I don't know if anyone really knows what it is, but heat, here's the big thing. Heat is a form of energy, folks. Okay, in very simple forms, heat is a form of energy. Now, for heat, it was actually made, James Joule was the first person to actually connect the idea of energy and heat. And so he did some experiments to see what can heat do, okay? Because the thing is, heat, if it's energy, should be able to do this thing called work, okay? And so he came up with a way in which to measure what heat could do, and he figured out, and again, if you develop a unit, you can name it after yourself, all right? And so he figured that to move a 1 kilogram mass, which is roughly about 2.2 pounds, folks, all right, a distance of 1 meter in 1 second, this is what he classified as a joule, or 4.184 joules, okay? So it takes 4.184 joules to move a 1 kilogram or 2.2 pound mass, a distance of 1 meter in 1 second. Okay, so this actually started to make sense to a lot of folks, and so they decided to build off of that. And so looking at energy, all right, another unit was created, and if you notice, look, am I defying grammar laws? But no, I'm not. I put this as lowercase because I want you to understand that this is a chemistry calorie. And so they looked at it from water and how much energy water absorbs. All right, so a calorie, by definition, is the amount of heat needed to raise the temperature of 1 gram of water, and in particular, pure water, 1 degree Celsius. So there is a relationship between joules and calories, okay? And in certain countries, they don't use calories. They actually do use joules for measuring their energy values in food. And so a food calorie, as just a reminder, is equal to 1,000 calories, which is equal to 1 kilocalorie. So again, 1 food calorie is equal to 1,000 chemistry calories, which is equal to 1 kilocalorie. All right? And again, don't forget, the food calorie was developed in America, so because we don't do metric. Okay? Now, the relationship between joules and calories is that 1 calorie is equal to 4.184 joules. Now, you're going to ask, Mr. Smith, do I have to memorize all this? No, you do not have to memorize all of this. This would be given, all right, given on an exam. Okay, everyone got that? This would be given. You would not have to memorize it. You would just need to know what a joule is and what a calorie is and how they're different. In order to abbreviate a joule, we use a capital J, and in order to abbreviate calories, we use a lowercase c-a-l. Now, here's an important concept. We have these things called laws, and they are different than theories, and they are different than hypotheses. Laws are things that cannot be broken, okay? So the law of conservation of energy states the following, and you've probably heard of it, that energy is never created nor destroyed, but just simply changes form, okay? It will just change forms, all right? So the amount of energy that we have on this planet, again, we're getting it from the sun. It's not that we're creating any of it. We're getting more energy, all right? And so energy is never created nor destroyed. It is just simply changing forms, all right, and transferring itself. Now, energy, however, is usually lost in the form of heat. And you're saying, well, what does that mean? When we look at energy, we want it to do useful work. We want it to be able to do something for us. And heat typically doesn't do a lot for us. But mechanical energy does a lot for us. So if we use the idea of a car engine, and when I'm talking about a car engine, I'm talking about one that uses this thing called gasoline. You know, the stuff that's costing on the order of like $4.62 per gallon. Oh my gosh, it just kills me. All right. But a car engine is only 37% efficient, meaning it converts 37% of the energy into movement. What does that mean? Well, that means, folks, that there are 63% of the energy is lost in the form of this thing called heat. Oh my gosh, how inefficient is a car? Think about how many cars we have on the roads that run on gasoline. Now, when you start talking about other cars like Teslas or electric vehicles, they're a lot more efficient because they're not wasting the time of doing combustion to create the movement. Okay, they're using batteries in order to do that. And so there's a little less heat, but there's still residual heat given off. If anyone knows anything about Teslas, they got to keep the batteries cool because the batteries get hot. And that heat is lost form of mechanical energy. All right? But the idea is that energy is just simply transferred. It cannot be created, nor can it be destroyed. Now, here's the thing. Energy interacts with matter differently depending upon how the molecules are arranged. And so we call this item in which energy interacts with matter specific heat. And what specific heat is the heat required to raise 1 gram of a substance by 1 degree Celsius. Doesn't that sound familiar? Didn't I just kind of say that? I did that in reference to water, didn't I? Okay? And so every substance has its own unique specific heat. So here, folks, is a list of substances with different specific heats. So we can see here water in its liquid form has a very high specific heat compared to ethanol. Okay? However, if you look at gold, gold has a very, 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 very low specific heat. So what does it mean if something has a high specific heat versus something that has a low specific heat? Well, the lower the specific heat, the less energy that is required to increase the temperature of the substance, meaning it will take in the energy faster and it will increase the temperature faster. However, if something has a high specific heat, like water, it takes a lot of energy, tons more energy, in order to increase the temperature by just 1 degree Celsius. All right, so things that have high specific heats do a great job of storing energy. This is why our planet, thank goodness, remains warm in the evening, because we have a crazy amount of water. So the heat that is stored in the water ends up being released overnight. And it ends up storing more and more energy during the day. All right, this is why we pick certain substances to be able to dissipate heat or transfer heat quickly. Okay, I don't know about you, but I like to use aluminum foil for cooking. And the reason I use it is because it does a fantastic job of dissipating the heat very, very quickly. If you're into computers, you know that there are certain materials that are better at dissipating heat than others. All right, and so this science, there's actually an entire branch of science devoted to the idea of materials and what we can use in order to reduce heat transfer and things like that. Okay, so what can we use specific heat for? Well, what we can actually use specific heat for is to calculate this thing called heat, or what we like to call calories, or, yes, wait for it, joules. Okay, and there is an equation that we use. All right, the equation is called Q is equal to M times C times delta T. Okay, each one of these variables means something, and you're going to ask yourself, oh, there's an equation, what do I do? You don't have to memorize, you just have to know how to use it and when to use it appropriately. So let's go over each one of the variables. So Q represents heat in the form of joules or calories. Remember, J here represents joules, lowercase cal represents calories. Okay. On the other hand, the M stands for mass in grams. And we always use grams for our mass. Okay. The big C, that actually, delta T means the change in temperature. And change in temperature is always the final temperature minus the initial temperature. It's always the final temperature minus the initial temperature. It's always the final temperature minus the initial temperature. Did I say that enough? Okay. And then we have C, which is specific heat. Now, the units for specific heat are joules per gram times degree Celsius, or calories per gram times degree Celsius. Maybe you saw this. Maybe this was found in question number 3 on the calorimetry lab. Okay, so the idea is that if we know these variables, we know, for example, the mass, if we know the change in temperature and we know the specific heat, we can actually solve for the Q, the heat, the joules or calories that are absorbed or released by a substance. Okay, so again, remember, specific heat is the heat required to raise 1 gram of a substance by 1 degree Celsius. So let's go ahead and, and it's specific to the substance. So let's go ahead and try using this equation. So let's take a look at a sample problem and walk through it together. So the question is, how much heat, how much heat, that means we're trying to solve for Q, is required to raise the temperature of 200 grams of mercury. So they're telling us flat off the bat that our mass is 200 grams, and it happens to be a substance called mercury, 50 Celsius degrees. That means that our delta T, folks, is 50 degrees Celsius. And they gave us the specific heat of mercury as 0.15 joules per gram degree Celsius. So we are going to be using the equation of, and Q is equal to M times C times delta T. So let's write down what we have. We have specific heat, which is 0.15 joules per gram degree Celsius. We're trying to solve for Q. We have our mass of 200 grams, and we have our change in temperature as 50 degrees Celsius. So knowing all this, we can actually use it and plug it into the equation of M times C times delta T, okay, where Q is equal to M times C times delta T. So I plug in my values here. So I have my 200 grams times our 0.15 joules per gram degree Celsius times our 50 degrees Celsius. Make sure you look. Grams are in the numerator here. Grams are in the denominator here. So gram divided by gram is 1, so they cancel out. Degrees Celsius here, degrees Celsius here. One is in the numerator, the other one's in the denominator. Dividing each other, they would come out to be 1, so they cancel out. So my answer here, I would end up with as 1,500 joules. So what you're going to be doing is working on the calorimetry or heat and energy worksheet here in class and answering the questions based upon the notes. Good luck.